Morning, good afternoon, or good evening, depending on where you are. Thank you so much for joining us. My name is David Cantor. I'm one of the founders of MLCommons and the head of MLPerf. Uh, this is going to be the MLPerf Inference 6.0 press briefing and just a couple of housekeeping items. All this, the content discussed here, any of the information here about who submitted, what the results are, et cetera, is under embargo until April 1st at 8 a.m. Pacific time. This is material non-public information for those of you who do interact with investors. So you've been warned, and you treat it as such. So if we want to, as Scott said, we've got a really packed agenda here. You can see all the speakers up on the screen here, and let's go on to the next slide. Yeah, perfect. You're reading my mind. Fabulous. And then also, I'm going to ask if folks who aren't speaking, if you can mute just so we don't get any stray noises. And we'll take questions at the end. So as per standard procedures, all of the briefing materials will be available on Google Drive. The results should have been shared with you. We've got results, supplementals, press release, and then the team's done a fabulous job of pulling together blog posts describing all of our benchmarks in a fair degree of detail. Those are also going to be shared or already shared via Google Drive. So any questions, any materials you want, check this link. If you're a member of the press or analyst community, it should be in your email. Next slide, please. So this is the agenda. I get to do the overview, and then we will be passing it off along for various folks here. Next slide. Everyone knows who I am. Next slide. All right, there we go. So just a bit of a reminder of who we are. MLCommons is a 501c6. We are a nonprofit industry consortium bringing together over 125 members. And one of our marquee projects is MLPerf, which is simply put the benchmark of record for AI system performance and efficiency used all across the industry. And on the right side of the screen here, you can see some examples of how some of our member organizations use our benchmarks in educational marketing materials, talking about their systems and so forth. And, we are thrilled to have this level of wide participation. Next slide, please. One of the things I want to talk about is sort of the principles behind making a successful benchmark. And I think I've really tried to identify and boil it down to these four things. Relevance, important workloads that people care about. We want to be testing the most important workloads out there because as we test things, people will start to optimize them. And that's kind of what drives the engine of progress. Well, part of what drives the engine of progress for the industry. We want our benchmarks to be fair and neutral. That requires a huge amount of technical carefulness and maturity. That's been one of the hallmarks of MLPerf from the very early days is, we wanted a benchmark where everyone would be on a level playing field from startups to CSPs to silicon providers to OEMs. And that requires a fair bit of rigor in the rules and so forth. We want the benchmarks to be reproducible. That enables sort of it's part of what transforms it from, just a marketing exercise, which benchmarks can be, into the promotion of best practices. If you're a submitter, if you're a buyer, you can reproduce MLPerf results because all of the artifacts are in the submission repo. And that enables you to reproduce what's going on. And then, you can look at a submission, if you're a buyer, you can look at a submission by a vendor and say, hey, this thing doesn't quite map onto my system. And so even if you can't fully reproduce it, you can start to understand those differences. And that kind of reproducibility is part of what drives trust in our results and helps them to be the industry standard. And then you want to be inclusive, right? So part of this is by working through an industry consortium, through a 501c6, we have very clear rules on everyone can participate in the formulation of the benchmarks, in the review, and it is a very robust process that drives a large degree of community engagement. And that is how you help to build an industry standard, is by including a large swath of folks. Next slide, please. So, one of the things that I'm really thrilled about is there's a great quote here on the right side of the screen from the National Lab of the Rockies. It's formerly NREL, but it was recently renamed. And they were out purchasing a system for their internal use. And the thing I just want to highlight is, for them, it was clear they were going to be using MLPerf, and really the question was, which benchmark within the suite would they be using for procurement, right? MLPerf is absolutely used to drive buying decisions. We have tens of thousands of results. We've seen it used in RFPs for everything from smartphone silicon to large-scale data centers. And MLPerf and MLCommons has been recognized by many standards defining organizations like ISO, IEEE, and so forth. And then actually one of the things I want to highlight is MLPerf, we collaborate with folks all throughout the industry to help create new benchmarks. And so these are data providers, these are model providers, and without stealing anyone's thunder, many of the benchmarks that we have here were external collaborations with third parties, and I'm really proud of that. So I think with that, on to the next slide, I get to hand it over to Miro Hodak, who is one of the co-chairs of the working group. So okay. Miro, take it away.
Absolutely. Thank you, David. So I'm the co-chair of the MLPerf Inference working group. So this is a group of folks that representing companies that normally compete in the field that come together to define what are the benchmarks that fairly represent the current workload seeing in the field, and we define the benchmarks and also run the benchmark execution. And this is what you will see today. We have I will walk you through some of the new tests that we have. And also give you some of the quick overview of the results and trends that we see from the results here. When I look in what we have in the MLPerf Inference this round, I think we can easily consider it our best round yet. We have updated or changed almost half of our workloads in our popular data center benchmark suite. We have the largest scale submission that we ever received. We also have record number of multi-node systems, and we also have, as David mentioned, collaboration with other partners in the industry that contributed key features into some of the benchmarks that they use in their business. So with that, let's get into it. So MLPerf Inference, as I mentioned, this is a benchmark suite. So it has multiple sub benchmarks that has a goal of measuring a machine learning system performance, and we want to do it in sort of neutral, representative, and fair manner. That's why we sort of have. It's very valuable that we have different folk representing different companies coming together and defining this. We cover both data center and edge systems, and really the goal is to measure the performance and gain, and move the field forward with this, because then systems can be improved to have system. By that I mean both hardware and software can be improved to further get better in this test. So let's move forward. So the way it works is actually the way we currently do any of the tests you're going to see right now has not changed really since the beginning. So it's fairly simplistic, but it's very powerful as well. You basically define a system. You define an input, then you feed it to the model, and then you check what the result is. You need to have certain accuracy, certain quality, but then you actually measure how quickly you can generate these results. We are actually currently have task forces underway that want to change this. We have a task force on end-to-end AI that would have multiple components in it. We also have started a task force on multi-turn that will sort of move the field towards more of the modern trends, perhaps touch on some of the agentic workflow. But again, anytime you want to define more of the complex things, there is more things to define, and the benchmark becomes the benchmarks become more complex to do. But that's one of the things that's coming in the future, because that's what's happening in the field. When you look into the results, you will see that there are multiple divisions. We have a closed on open division of the results. Closed is called closed because there are strict rules, and all the results have to stay within those rules. What this enables is apples to apples comparison. So anything you see in the closed category can be compared to one another. On the other hand, open allows submitters to change some parts of the submission. It could be that they change the model. It could be that they do things to the model that's otherwise not permissible, such as pruning. And then sort of they can displace the results there as well. They need to identify what's the difference between in their submission, but that sort of allows additional creativity and showcase of additional features on top of what you can see in closed. We also have, I will also remind you that the results that you see is sort of the MLPerf is a full system benchmark. So it's not that we measure hardware on its own, but we measure full system that is hardware plus software together. Let's go forward. So you also see that we evaluate inference in multiple different ways, and that's because there's multiple ways how you can do that, how you can measure it. So I guess the basic one is offline, which is really a type of scenario where a batch of data is presented to the system, and we simply measure when it's done processing. So this is really sort of raw throughput, sort of measuring raw capabilities of the hardware for throughput type of measurement. Now, in reality, oftentimes we have online type of scenario where query arrives with certain frequencies, and that is what our server and interactive scenarios do measure. In this case, while queries are arriving, they need to be resolved. They need to be returned within certain latency, and the result is again throughput, but sort of like latency bound throughput. Then we have single stream and multiple streams, which up until now have been only part of our edge systems. However, in this round, we see that single stream is actually part of our text to video benchmark, and this is the first time in the data center system. And that is because this is simply a different type of benchmark. Generating a video is quite a bit of time consuming, let's say answering a question in a chatbot, and because of that, it makes sense that once a query arrives, the entire system is generated to that, and that's how you can do processing. I think we can go to the next slide. When you look into the result that we have in 6.0, and when we sort of create a matrix of all the possibilities, so when we have closed open division versus the status of the system, which can be available, preview, or RDI, you can see that our results are heavily skewed to the one cell. This is the closed division available data center, and that's sort of traditionally where we have most of our results. The good news is that these are the results that can be compared to one another. So this sort of gives an opportunity to do so. So we have a wealth of data that can be used. We also have submissions in other parts, which is always good to see. We have a few edge submissions. We also have on open division submissions as well. Let's go next. Now, I mentioned that we had updated quite a few of our benchmarks, and in fact, the amount of new benchmarks and the level of update, this is by far the most we've ever seen. In the preceding rounds, 3 was the most that we have done. In this round, we have actually 6 new entries in here. In our data center, I think we have 11 benchmarks. We have 5 of those being updated, and in Edge we have a new benchmark. So this is a substantial effort and substantial turnaround in turnover in our data center in order to keep up with what's happening in the industry. Now, for each of these, we will have a task force leader. We had task force for that was actually working on each of these updates on each of these new benchmark. You will hear from those to giving you the details. One thing I want to show on the next slide, please, is the update we've done in DeepSeek. So DeepSeek, we had defined DeepSeek in our previous round, 5.1. What's new in this one, we actually extended to define interactive scenario, but within the interactive, for the first time ever, we have allowed speculative decoding. So we define the rules under which speculative decoding can be used. And in this round, if you look into interactive scenario results, you will see the results that incorporates speculative decoding, and this is something that we look forward to do for the future benchmarks as well. Let's continue. We have mentioned that we had several important leaders' contributions to benchmark creations, and specifically it was from these 3 companies. We have from Ultralytics that helps us with YOLO 11 model. So this is a modern model for object detection. We also have Shopify working with us on our visual language model to give us so that we can use a product catalog data set for these benchmarks. They help us with curating the data set that is being used for this actual benchmark. And also we have Meta leading our task on the LRM v3 update. So this is a state-of-the-art recommender models. We usually recommending models don't get a lot of attention these days, but they are still critical. But they are a critical piece for revenue generation for many large companies. And because of that, having a public model is very important, because lots of these recommended systems are often proprietary. So we are happy to have this one and have a long overdue update here. Let's move forward. Then another sort of part of new things here is that we have recently done a demo of MLPerf endpoints, which is another way of measuring inference, but more from a perspective of serving generative AI. And for that, we have created new infrastructure, which we've written a key part of our benchmark. So we have a new version of our LowGen called LowGen++. And continue working forward, we want to make sure that we can sort of share lots of things between these 2 types of benchmarking suite. And for the first time here, we have an adoption of endpoint infrastructure for a submission. Specifically, that's Intel who has submitted an open division results using this tool. So let's move forward. When we now I'm going to just look at what we have, give you a quick overview of the 6.0 results. We have 24 submitting organizations, and overall we have 504 results across data center and Edge. I want to specifically call out 3 of our new submitters. This will be Inventec, Netweb, and the Stevens Institute of Technology. On the next slide, let's dive into some of the results. So if you look at benchmark participation by numbers, so out of these data center benchmarks, we can see that Llama to 70 billion continues to be the king of our benchmarks. This is obviously not the latest benchmark, but benchmarking community people who are interested in submitting the benchmark are somewhat conservative. Is that because there is a value of measuring something that is still a good proxy for current benchmark, but also gives you something where you have a history, where you have some sort of historical record. You can compare performance across multiple generation, and you have wide range of comparable data, and that is exactly where Llama to 70 sits. Now, speaking of Llama to 70 historical comparison, I can show you that on the next slide here. So if you look at performance improvement over time, and this is the benchmark that we have since 2004. So this was sort of the round that we had 2 years ago. If you look at that, we can see that we can see also on the plot the number of tokens generated has definitely increased a lot. If you look at what's the median per accelerator performance improvement since the inception of this benchmark, it's 4.6x, so almost 5x improvement. However, what's even more staggering, if you look at actually the highest score improved, so if we don't look at it per accelerator, but as a system measure, we have astounding 34x improvement. Now, where this comes from? This comes from obviously that we now see larger scales, and I'll show you a bit more on that. We also have new generation accelerators since then. We are not, what we measure on 4.0 is quite different what we measure right now, and we also have wide adoption of FP4 inference, which in FP4 inference, and that brings a significant performance benefits. And pretty much now, if you look into our results, most of them, especially in large language model, have been generated using FP4 numerical precision. Let's continue. So one of the sort of exciting things that we see here is that there is last couple of rounds there have been significant embracing of multi-node inference. If you look previously in this 4.0, in the time when we introduced Llama to 70 billion, there were no multi-node submission. And if you look more before that, there was for a long time, we haven't really had any. Then we started to see an occasional here and there. In previous round, we had 10 multi-node systems. Now we increased it to 13. And if you look at actually what is the largest scale, we have the largest scale ever. And in this case, that's a submission that has 72 nodes and 288 accelerators. So this is by far definitely the record. But what this speaks to is definitely multi-node and distributed inference is something that gets more and more interest. And that's where our submissions, that's reflected in our submission. Let's continue. So this is my last slide. So far, I was covering the data center, which is where we have most of our submissions. But definitely, edge is also very important. There are a lot of edge systems and interest in it as well. We have the new YOLO benchmark that task force have created for our edge, and this happy to say that it immediately went into being the leading benchmark in our edge within our end benchmarks. And with that, I'm going to now open it for our task for leads who will walk you through individual of this new benchmark I briefly mentioned and give you some of the details. The first one is Virat, who will talk about GPT-OSS benchmark. Virat, please take it away.
Thanks, Miro. So new to this round is the GPT-OSS 120 billion parameter workload. It's a mixture of expert style model. Next slide, please. Yeah, it's a mixture of expert style model with the reasoning ability. It comes with about 117 billion total parameters, of which about 5.1 billion are active at any given time. We added this model based on its popularity among the open source models at the time, and its popularity among diverse use cases particularly. We aim to test this model, evaluate its accuracy on diverse high difficulty data sets, which comprise of questions across math, coding, and science. We also aim to evaluate its performance at practical speed targets for real deployments. To achieve this, we leverage the reasoning effort introduced by GPT-OSS, which is a new way of controlling the amount of tokens, the token budget available to the model to answer questions. We use the low reasoning effort for routine mundane chats, and we choose to use the high effort for the difficult knowledge and reasoning questions. Next slide, please. So we have decided to use separate data sets for accuracy and performance measurements for GPT-OSS. For the accuracy test, as mentioned, we are using the high reasoning effort. The question comes from science, code, and math from the GPQA Diamond dataset, Life Code Bench, and AIM. The metrics used here are exact match on the answer, which means a given sample can be pass or fail. On the performance test, we use the low reasoning effort, and the task is summarization of articles from the PubMed dataset. The latency targets for this performance test are for server scenario, we have 3 seconds P99 TTFT and 80 milliseconds P99 TPOT. For interactive, we have chosen 2 seconds P99 TTFT and 15 milliseconds P99 TPOT. So that's it for GPT-OSS. Let me hand it over to Linjan, my colleague for DLRM v3.
Thanks, Virat, for the introduction. Hi, everyone. My name is Lin Jian. I'm a task force chair for the DLRM v3. Next slide. DLRM v3 is the new recommendation benchmark, and is also the first recommendation benchmark that includes generative or sequential recommendation. It includes a HS2 model with 1 TB model size and 260 TFLOP per second, TFLOP per example compute cost, which is significantly much larger than the previous versions. The design of the new benchmark is consistent with the industry trend, where we are switching from the wide and deep neural network for the recommendation to the sequential and generative recommendation. And also, as seen in the right two figures, the scaling law is also observed in the sequential recommendation compared to the previous architecture. The goal of this benchmark is to capture the dominant compute patterns of the modern sequential recommendation workloads. Next slide, please. Here we choose HS2 as our backbone model. This due to two reasons. The first is that the HS2 model, which is published in 2024, is one of the most popular generative recommendation models. And also, the introduction of this model introduces rapid adoption in industry across different companies, and we see many follow-up work papers based on the HS2 architecture. And here we show the different models architecture between DLRM v1, v2, and v3 in the bottom figure. In terms of the dataset, we use a synthetic streaming dataset. For recommendation, one issue of the existing public available real dataset is that they are usually too small and not very consistent with the workloads that are deployed in the production. So due to that, we use a synthetic dataset to make the workloads consistent with the production. The synthetic dataset has long user item history per request, so that the sequence length used in the example is pretty long compared to the production workloads. And then we have a very large item set, so that using large embedding table makes sense in the benchmark. We also use a streaming setup, which is consistent with the evolving user preference and also timestamp oriented inference replay. Next slide, please. In terms of the performance targets, we have two scenarios, offline and server. For offline, our goal is to maximize the query per second QPS without the latency constraint. And for server, we will maximize QPS under 80 milliseconds latency constraints. So both scenarios are important in production, and we will benchmark them here. In terms of accuracy, our goal is to maintain 99.9% reference accuracy and the normalized entropy and the AUC. So these three matrices are all important, and our goal is to make sure that our submitted model is accurate in all these matrices. In terms of challenges, hitting strict P99 latency for recognition models can be challenging, especially the latency constraint is pretty strict compared to other workloads. And also, we need to respect these streaming constraints while we are doing the batching and reducing the cache in the inference optimization. Finally, recognition models usually have very huge embeddings, and the fit and serve these embedding tables can be a challenge. Yeah, that's it. So next slide. Yeah, next I'll hand over to  尚 Wang, who is the task force chair for VLM.
好，谢谢 Linjan。那我们现在来看一下 GPT-OSS 1.0 的 demo。那么 GPT-OSS 1.0 是一个 Thank you so much, Lin-Jen, for the warm introduction. And hello, everybody. My name is Sean, and I am the task force chair for the vision language model benchmark for the V6.0 rounds. Next slide, please. So humans are inherently multimodal, right? So not only we can read or write, but we can also see, hear, and as well as smell. I wouldn't say as a result, but AI models these days are also becoming increasingly multimodal. And this is one of the most transformative trends that is happening in both the industry as well as the academia. So in the industry, market research has shown that the global multimodal AI market has been expanding. So right now we are at 2026. And the global multimodal AI market is estimated to be almost $4 billion US dollars. And then the same market research has predicted that by 2031, the global multimodal AI market will be way above 13 billion US dollars. At the same time, we're also seeing that multimodal AI models are being deployed in production use cases by manufacturers, such as hyperscale e-commerce vendors like Shopify. Next slide, please. In the academia, we see that there's a growing interest among theory and algorithm practitioners who essentially focus their times on multimodality. But meanwhile, we don't see as much attention on system-level performance optimizations efforts for multimodal AI models from the system and architecture communities. So in the examples on this slide, you can see that in top ML conferences such as ICML and iClear, the number of papers on multimodality has been quite noticeable and significant. But then if you look at top system venues such as MLSys, the number of research that are done on multimodality is not as significant compared to the number of research that are done on like regular like LLM serving performance. So this contract in terms of interest between the system architecture community versus the ML community basically motivate us to kind of curate a benchmark for multimodal AI models in order to kind of get more attention from the system and architecture community to kind of look into this area. Next slide, please. So the model that we pick for this benchmark is the Queen 3BL with 235 billion total parameters and 22 billion activating parameters. And this is the first time the Queen model, a model from the Queen model family, is being introduced to the MLPerf Inference benchmark suite, and also being part of the close rounds submission. So the reason why we picked this model is due to the Queen model family's widespread adoptions and downloads, and their state-of-the-art response quality, as well as the fact that this particular model has the MOE architecture, which is kind of the mainstream architecture adopted by top open source models these days. And also it has a practical number of total parameters as well as the number of activate parameters. Next slide, please. So for this round, we are very fortunate to collaborate with Shopify to craft a benchmark that would mimic their production workloads. And then as a result of this collaboration, on the right-hand side of the slides, I'm showing the Hugging Face landing page of the data sets that we're using for this benchmark, which is called Shopify/products-catalog. So from a high level, the task of this workload is that the inputs are the titles, the descriptions, and the image of a particular product. And basically, we're trying to ask the model to categorize this product into with the most appropriate category out of a list of potential categories. So this is like an inherently kind of throughput-oriented workload. So the performance matrix in this case will be samples per second, and then each request will contain a single sample. And then the server scenario, the 99 percentile latency constraint for the server scenario will be like 12 seconds. So this mimic the use case where Shopify kind of like hit a like a surge demand during like holidays or like Fridays, where like essentially some of the processing happen online as opposed to offline. And then the accuracy metric that we use is hierarchical F1, which is designed to compare, I guess, evaluate partial matches between two category hierarchies. So next slide, please. So with that, I would hand it off to Ting Yin to talk about text to video.
Yeah, thanks for the introduction. So I'm the co-chair of the text to video benchmark. So this is a new benchmark, and our video generation has several goals. One is we want to have the video have like high accuracy, and it can be widely used in like healthcare, financial, legal, and use it as common as possible. And also, I want to make a deployment to be very diverse, and that can be capable of like a wide range of hardware and software stack. And our goal of the performance is throughput, which is query per second. It does generate the output frame to several output frame and then into video from a text prompt. Next slide, please. Yeah. So here is some details of the benchmark. So this benchmark is 1.2 text to video, a 14B diffuser, which it has like 14 billion soft parameters. And we, for the data set itself, like we use the subset of the vBench. vBench is open source data set that helps us to evaluate the accuracy and yeah, and like it we make a subset that has 248 prompts and we average over 6 dimension of the vBench to help us to do the accuracy evaluations. The reference accuracy is 70.48, and we do have like 9% of the threshold, which is very similar to other benchmarks. And like the scenario we provide is offline and single strings. So here is one example with the prompt that about selling leisurely along the Seine River with Eiffel Tower in the background and pixel art. Yeah, this is one of our example output. Yeah. Next slide, please. In this benchmark, this is like high levelly what we do. So the input is our prompts and latent noise, which is a series of frames that are in like noise. Yeah, and the prompt will fit it into UMT5, and then the output will be text embedding. Text embedding, and then the text embedding will fit it into our high noise DIT and the low noise DIT respectively. The latent noise will fit into the high noise diffuser DIT encoding for encoding. And after the computation of like in the latent space, like the output of the diffusers will fit it into the VAE decoders, which will help us to reconstruct pixel by pixel videos, frames to frames from the latent space, and generate generate videos from the from the output. Yeah, this is like what we do, and I want to have a special thanks to another co-chair, Ashat. Yeah, and next slide, please. Let me hand it over to the YOLO chair, MLPerf.
Thanks, Tin. Yeah, I'll be going over the YOLO work that we did for upgrading the RetinaNet benchmark. The goal of this was to basically replace one of the legacy object detection workloads, RetinaNet, with the Ultralytics YOLO v11, to kind of align with upgrading and staying up to date with the latest industry models. So we'd like to first of all thank Ultralytics for the model support. And kind of the main reason why we chose YOLO. It's the modern standard. It's one of the it has very strong community adoption, and it has very frequent releases. As we were making the development for this work, we also looked into the most recent release, which was YOLO 26. But YOLO has been a standard from some of the great models from YOLO 3, YOLO 8, and YOLO 11. They've been very trusted and very adopted very frequently in the industry. Some of the things that we looked into the different types of model variants that are present for YOLO v11. There's different sizes: nano, small, medium, large, and extra large, and we decided on large based on parameters, the parameter size, fitting that into different servers, basically different GPUs. And we also looked at MAP, right? The MAP is the mean average precision. It's how we're calculating and dealing with accuracy on the COCO data set. So MAP will basically calculate that average. It'll calculate an average of the average precisions across multiple classes. So if you think about it, the goal of the YOLO model is to identify and basically put into a class an object inside of a certain image, and then over a certain number of thresholds, over a certain number of basically predictions, is this the correct what confidence with what confidence is this the correct class? And yeah, that MAP score is within 0 to 1, and I'll speak a little bit more about it in the next slide where we talk about data set. So yeah, the data set, an important part about this was making sure that the entire data set is distributable to the entire working group and everybody involved in MLPerf. So we had to ensure that the licenses and each of the images were non-commercial. So in order to address that, we created a filtering pipeline to kind of extract the safe images and create a safe subset of the images. But one thing that we did was to ensure the accuracy is still at the same level, right? So at the full data set versus the safe data set, we ensured the accuracy is correct across the whole class of the different classes, basically all the 80 different classes. And yeah, the impact is to make sure that we have a benchmark that's fully distributable both in academia as well as industry without any compromise to that MAP score. And moving on, we'll speak just a little bit about what the performance itself, the different scenarios. The Edge benchmark comes in has three different scenarios: offline, single stream, and multi-stream. Similar to the data center suite, offline measures peak throughput in terms of samples per second by processing the entire data set at once in a single batch. Single stream, you're looking at the absolute minimum latency for a single inference, a single image. Multi-stream creates multiple different channels, 8 channels, and sends it to the system under test, the SUT, and it'll basically calculate the scores based on that. So another interesting part of this was during the task force, we had a discussion about two different accuracy scores. We have YOLO 95 and YOLO 99. Typically 99 is default and 99.9% is the high accuracy version, but we decided to have YOLO 95 as well as YOLO 99. The YOLO 95 threshold serves as a default mode, allowing for submissions that prioritize speed and throughput using the standard production needs. YOLO 99 we thought would represent our high accuracy, and it would be for mission critical applications. So it's a lot closer. The accuracy targets itself is closer, and we got those numbers based on multiplying 0.95 by the accuracy number reported by YOLO v11, and YOLO 99 0.99 and 0.95 respectively for those two modes. And yeah, I would like to thank everybody who's involved in this. It's in the YOLO task force, all the people involved. It's a great positive step forward to reflect and basically ensure and upgrade our benchmarks and ensure that it's in the latest most industry relevant benchmark for the community. And with that, we will be open to taking questions from the group.
All right. Thank you so much, Manpreet, and thank you to everyone who worked on this. One of the things I just want to emphasize is, the speakers here are often leads of the task forces. There's many other people behind them, and there are a lot of other people behind the scenes contributing here. Everyone from IT to marketing to program management and product management. MLPerf is 100% a team sport, and it takes a huge team to make it happen. So thank you all.